All right, let's restart. I hope everyone can hear me in the various platforms, including live. So it's a second lecture, and we'll recap a bit what we did yesterday. You already did this with Nuriya, so we go a bit faster through that. And then we'll talk a little bit more about measurements, about different types of measurements, about what happens to the quantum state after we measure it. Okay. So I'll just recap what you by now you've seen a few times. So we represent the quantum state of a system by a ket in a Hilbert space, so an element of a Hilbert space. And in the discrete case, we can expand these vectors as some sum over some basis elements of some coefficients, and you could call them anything. And I'm going to call them phi of x just because it's similar to what we'll see later. And now remember that these are columns. These are columns. And these are just numbers, right? So these are just complex numbers. And these are the basis elements. And this is, for discrete cases, we normally just call it the coefficients, but we can call it the wave function. And the key thing about the wave function, which we'll see later also in the continuous case, but not for now, is that it depends on the basis, right? We saw that if you express, for example, a qubit in the 0, 1 basis, the coefficients that appear here are different than those that if you express it in the plus minus basis. Yep. Okay. And what makes them a basis is that they span the whole Hilbert space. In the continuous case, we saw that we can express it as same thing. We just replace the sum with an integral over some limits which depend on the space that we're talking about. So we talked about the particle in a line, and then it went from minus infinity to plus infinity. But you could also think of a space that it's finite, but just continuous, right? So it goes between two limits. You know, for now, these are just made up spaces. They don't represent anything physical yet. So you can put whatever you want there. That's the wave function. And it's exactly the same, just with an integral instead of a sum, right? And then how do we get the wave function in both cases? We can get it by just taking our state and doing the inner product with the basis element, right? And the other thing we described was the inner product. And for any two states, it's just kind of a sum of, this is in the discrete case of x over basis elements, or in the continuous case, it's the same just with the integral, right? And again, here's the integration limits. Good. And the last thing we said is that all these states, we consider them to be normalized. And this is again just so that our probabilities make sense when we do measurements. And that's just this condition. Oh. Okay. The last thing we said yesterday, and that we'll do a bit more, was this rule for when we measure something with respect to a basis, we take a quantum state, which we'll talk about how to do it in a lab, and we say, well, we want to measure it in some basis with respect to WRT. some basis x, then this is true in both cases, both the continuous and discrete cases. What's the probability? So this notation means probability of getting outcome x when I measure state psi. And we saw that this was given by this inner product squared. And if this is the basis element, this corresponds to this, to the square of the absolute value of the wave function, right? This notation, we'll see later that when the state is obvious, we drop it. When the cat is obvious, maybe we just put here the outcome, so we put just x instead of the cat. In some cases, it will become a bit simpler. Okay, but so far, this is what we did last time. And I'll do some examples because I have not done. And I found an example that where the probabilities work out very nicely. And I'm not sure if you did this in the tutorial because I wasn't here, but let's do an example of measuring a qubit. So we have a qubit. And let's kind of for the first time plug in numbers that are not just square root of 2. So suppose you have this state. So it's almost 0, but has a small component of 1. Right? It's normalized because if you do the square of this plus the square of that coefficient, you get 1. And if you want to represent it on a block sphere, well, so I saw that Nuriya puts the x-axis here. I did it the other way around, but you know, as long as we're consistent within each block sphere, it's okay. So here's the 0, here's the 1, and then this is kind of a little bit here. So in this direction, coming towards the outside of the board. Right, so here's my state. It's almost 0, but it has a little component there. So for the records going in the y direction, this is when you start adding complex numbers here. Then you get, then you go in the y direction. Okay. So it looks like this. And now let's do very simple. We just measure it in the z basis. Does anyone want to guess what the probabilities will be? So this is, I want to measure in this basis. Any guesses? What the probability will be of getting outcome 0? Where it is? Yes?
0.9.
Yeah, it's going to be 0.9. So let's just do it explicitly once. So you can read it directly because the state is already written in this basis, right? But we do it explicitly, so it's this inner product. And now let's expand this. So this is 0, and psi was what? Square root of 0.9, 0, plus square root of 0.1, 1. And now it's just distributive, right? So it just goes inside. Square root of 0.9. Now we have this in the product, that's 1, plus square root of 0.1. This in the product, which is 0. So this is 0, and this is 1. So you end up with square root of 0.9, which squared, so that's 0.9. If you do the same with 1, not surprisingly, you'll get 0.1. So let me just write it. So the probability, of 1 with the state is going to be 1 psi square n. really easy. Like when the state is written in a basis and you want to measure it in the basis, just take the coefficient and square it. Now, more interesting is to say, oh, what happens if you want to measure it in the x basis, for example? And I could measure it also in the y basis. It's just that to do it in the lecture, we don't want to carry all this complex numbers around. So now we measure in the x basis plus minus. So what's the probability of getting plus when I measure this? Again, just in a product, squared. And now we need to expand both sides, right? So this is 1 over square root of 2. Let me put this outside the bracket. These are bars, not cats. 0 plus 1. And now 0.90 plus 0.1. 1. Chuk, chuk, chuk. Right? Okay. What does this give us? Also, now we have we're going to have 4 in a product. So I'll just expand them. This 1 square root of 2 is multiplying by everything, so it can come outside. So you just have 1/2 of all this thing inside. So let's see, we have 0.9. 0, 0 plus 1, 1. Sorry, plus 1, 0 plus 0.1, 0, 1 plus 1, 1. Okay, and now let's kill the orthogonal ones. So this is 0 and this is 0. So we have these two survivors, right? 0, 0 and 1, 1. So what we end up with is, second, 1/2 of square root of 0.9 plus square root of 0.1 squared. And this looks like it's going to be some horrible number, but turns out to be just 0.8. I thought I'd made a mistake in the when I did it because it looked too nice, but it's this. Okay, so you can do the same for the minus state, and it's going to be, of course, 1 minus 0.8. So the probability of getting minus is going to be 0.2. So now what happens if I measure in a different basis? So I'll just write the last one because we've not seen the y basis yet. So the y basis, we call it plus I and minus I states, and they are defined. So plus I is 0 plus I1 square root of 2, and minus I is 0 minus I1 over square root of 2. So now at home, you can, 1, check that this fit exactly in the y-axis in the block sphere by computing the angles. And 2, you can do this probability. So exactly the same, you just plug in this states, and you're going to see that the probability of this of plus I is 50%, and of the other one is 50%. Of minus I okay, they're both going to be 50%, and if you look here, it's in the XZ plane, which you cannot see very well from my beautiful drawing, but it's on the xz plane, so it's not biased towards plus y or towards minus y, so it makes sense that it's 50-50. Okay, so that's just an example, but now you're probably wondering, well, what does this mean in practice? How do you go about measuring these things? And this is something that we will spend a lot of time doing in the lecture. But for now, I'll just make some drawings and give you some very quick examples. So the trick is most quantum properties, you don't measure them directly. What you do is you make them interact with something else. And at the end of the day, you measure some photons hitting a detector, for example, or some electric current somewhere. And so the other thing to keep in mind is this thing that Dirac said that, this, he didn't say qubits, but this qubits is like, think of chess, the idea of a knight or a bishop. It doesn't really matter what they're made of, if it's like a chat set made of marble or wood, or if it's on your computer that you're playing, they all behave in the same way, right? So in the same way, you can have quantum systems represented by the same Hilbert space, where in the end they have the same kind of dynamics in practice, but that correspond to very different physical systems. So one could be photons or electrons or a massive circuit, but they all have the same properties. So a qubit could be many things. And so in practice, in the lab, so these are some examples that we look at in the lecture. So it's usually indirect measurements. So for example, if your qubit represents the spin of an electron, electrons are not balls and they don't fly into nice trajectories, but this is just an idea. What people do, what is spin? We'll see later what spin is really, but for now it is something that interacts with magnetic fields. So it either likes magnetic fields or not. So what people do is, well, I shoot electrons that come with this velocity in this direction, and then they go through some region with some magnetic field. Normally we call it B. And because this property inside reacts to the magnetic field, then this particle will either go up or go down, depending on whether it's spin up or down. And then it will eventually hit a screen. And here in the screen, we see the electron coming in, and maybe there's some photoelectric effect, and we see a photon coming out. And we detect this, right? And at the end of the day, what we're detecting is the position, not the spin directly, but it's an indicator, right? Another example is like a photon, and there's a property of the photon that is also a qubit, meaning it also has dimension 2, and that's the polarization of a photon. This is like whether they go through your cinema 3D glasses or not. And then one way to measure it is to just make it pass in an optical table through some kind of polarization filter. There goes the photon, and if it passes, then you have a detector and says, oh, here's the photon, it passed. So it was like I measured in a basis corresponding of this polarization and that polarization. That would be the Z basis. It's like, okay, passed, so it's like outcome 1. Of course, like even when we have very good measurements that can measure one single particle, you cannot reconstruct the statistics from one single particle, right? So what people do is prepare many, many states, shoot them many times, measure in different bases, and then try to work out probabilities. Okay. Another one is if the spin is some internal degree of freedom of some atom or ion, then you excite this ion and see if some photon comes out. It's this kind of things, okay? We'll later go more into this. But what these examples have in common is that many times at the end of the day is a position measurement. And when we do a position measurement, like let's say here, I have my detector. And even if space is continuous, which we don't know, so we don't know if space is like a computer screen with like some pixels, that is the minimum possible distance, or if it's totally continuous all the way down. Okay. And one obvious reason we don't know is that we're never going to have perfect infinite precision measurement devices. All we can do is kind of, we have like little cells here, and we try to make them as small as possible, right? And then we see which cell lights up. Okay, but at the end of the day, they'll have some kind of precision like delta, and we don't do a perfect measurement in the X spaces. So we need a way to model this kind of measurements of finite precision. So that's the motivation for what to do here. So projective measurements. So it's a mathematical way to model measurements that are they're still very, very clean, unrealistically clean. There's no noise in them, but they have finite precision. Okay, so what we do is to define objects called projectors, and I'll explain what they are later. So let me give an example. For projector, let's say Px corresponding to one of these cells. So it's something that goes from X to X plus some delta. And then usual things. So let's just recap on what these are. So I told you very briefly last time that these were matrix elements. So let me just write here again, and then we'll go back to them. So first of all, we saw that the inner product, the probability of getting just one outcome X was given by this, and we can expand this. So the modulo square is this complex number via times its complex conjugate. So it's check. So we have that. And now let's just put some brackets here. Okay. So this thing here, this is a column vector. This is a row vector. Multiply that gives a matrix, and it's a very easy matrix. So in the discrete case, this thing looks like, for example, if in the base in which it's diagonal, it's like 0, 0, 0s, and then 1, 0, 0, 0, 0, 0, and this one corresponds to the position X. Right? So if X was 0, this one would be here. If X is 1, it would be there, 2, and so on. Yeah. This thing then multiplied by the row vector on one side, the column vector on the other side gives you a number. Yeah. So what we do in this case is to just generalize this. But now instead of this matrix with one perfect element, we're going to put this kind of flatter matrix. It's true in the continuous case, also in the discrete. So then what we get, that the probability of getting now the outcome corresponding to this projector, the matrix psi, is just same as before, but now we put the projector here. Now, if this was X, if this was that, then in this case, if it was in the discrete case, it should be like 0, 0, 0s, and then at some point maybe 1, 1, 1. Here, if delta is like, if it has this precision, right? Okay. Of course, in the continuous case, we cannot draw a matrix like that, but it's this idea. So it's 0 everywhere except in a small region. Okay. Yeah.
So for now, there's another question. The probability is not quite clear to me. Like how would we model, like, for example, the Gaussian distribution? Would we try to use like state psi to somehow incorporate?
Yes, so I will actually, my next example is a Gaussian distribution. So the question is, how would we model distributions here? So I'll do this in a minute. Yes. So let me just write this in a different way for the continuous case. And then we see where the distribution comes in. So in the continuous case, with that example that we saw there, so with that specific projector, so this was from x to x plus delta. And now here comes the psi. Sorry, psi times this. X prime. That. That's right, I think. So I just put the px in the middle. And now, well, this is just a sum, right? So I can put this psi inside and this one also inside. So I get the sum from x to x plus delta, dx took, and then we have but this in the products we already know from before. What are they? This is just a wave function, right? So this is of x prime, and this is the same, but just the complex conjugate. So then what we get here is the sum from x to x plus delta, the x took of the square of the wave function. So let's see now the example with precisely the Gaussian. So now say I prepare a particle and I managed to do it in the lab such that the particle is kind of well localized around some average location. And the nicer functions that we normally have for this kind of property of being well localized around some position that are still physical are these Gaussian wave functions. And we'll talk about them a lot, so I'll not go into a lot of detail now. Okay. But where's my example? So suppose that p of x, this is a function that has some kind of dependence on f that is Gaussian, and we'll look at details later. So if you don't know what it is, there's some x squared there, blah blah blah, some coefficients. What it is that if you can plot, here's x, and here we plot already the square of the wave function because it's a relevant quantity. So in this case, it will look like this, perfectly symmetric, as you see, okay? So it looks like something like this, and it will be more or less narrow, depending on the parameters of the Gaussian. And this whole area under here, it's 1, because that's a normalization condition. So now, what does that projector mean? So suppose it's P of x0, this goes from x0 to x0 plus delta. Suppose that this is our delta. It's the precision, and then that probability corresponds to this area here. Yeah. So in this case, the observable is just the type of outcomes, and what makes your probability distribution, what replaces the classical probability distribution, is the square of the wave function. So you can see the probability of measuring here is higher than the probability of measuring here, right? So x1 plus delta, just because this area is so much larger than that. Does that answer your question?
So yes, what is this?
No, it's not independent from the basis you measure. That's very important, yes. I mean, the Gaussian is special because it looks Gaussian in a bunch of bases, but in general, that's not the case. So this could look very nice in one basis and look completely silly. Yeah.
Somehow meet some prior, like which basis we need if we want to model Gaussian.
Yes, that's one. Yes, that's one way to put it. Yes, yeah. I mean, in practice, you have the state that you prepared, and it will have the wave function that you managed to prepare in the lab, right? We don't know what it is, and then we just pick the basis for it. Good. So that's an example of a projective measurement, but more general, both in the discrete case and in the continuous case. What the definition of projective measurement is you represent the measurement by a family of projectors. Let's just call the family K. These are matrices in your Hilbert space. And I say K because it could mean anything, and it's usually a finite value. Right? You only have a finite number of outcomes in your lab. Doesn't need to be, but the properties that they need to satisfy is that, well, to put it compactly, and put it like this. So this is the delta of the Kronecker delta. So when you multiply two projectors, if they are the same, then they give you again the same one. So p squared equals p. And if they're different, they give you 0. Yep. And the other thing we need is that the sum over all k's of pk is the identity. So what this condition here tells you is it's a noiseless measurement. You don't have kind of overlap between two outcomes. They really correspond to like a very clean splitting of the Hilbert space. Good. In this, what it does is making sure your probabilities add up to 1. So we can do this explicitly. So the sum over all k's of the probability of getting outcome corresponding to pk when I measure any state psi, well, sum over k of psi pk psi, and psi does not depend on k, so I can take it outside the sum. Sum over k psi. Yeah. Give me a second. The identity does nothing, so this is just this, and we said the state is normalized, so that's 1. So people use different notation for the identity matrix. So this is really the identity matrix, like ones. In the continuous case, it's just. In the continuous case, this would be, well, the identity matrix. So over all space of dx, x. Okay. From -infinity to +. So when I put the 1 like this with a double dash, that's what it means. Okay. So now we're missing one very important part, which is, so we know how to model now a bit more coarse-grained measurements. And this is not the end of the story, because in real life, you have a lot of noise in measurements. They can do different things to the state. And there's a more general way to represent them. But we don't need it for now. So instead, let's talk about what happens to the quantum measurement after, to the quantum state after a measurement. So what happens in like classical programming, when you read a variable, the variable had some value, you read it, it still has its value. Maybe before you did not know what the value was, but you did not change the variable, right? You have a read function, it does nothing to the variable. It just tells you what's there. That's in my most recent analogy, that's like I'm asking you, oh, is the baby asleep? And you just look in the baby monitor and see if the baby is asleep or not, but you do not disturb the measurement. You do not disturb the baby in any way, right? You didn't change anything. You just gained information. In quantum mechanics, that's not possible. So measurements are more like opening the door, making some noise, seeing the baby, oh, he's awake now. Okay. And then you ask, and now it's still awake. So it's something that is, that disturbs the system. And of course, everything in the end is quantum systems. So also when you measure a variable, in the end, there's something happening in your computer at a hardware level, or where there's some quantum interactions going on. So you are disturbing the system, but there's just enough redundancy. You know, like you have 100 spins pointing up and you measure a very, very smooth property. There's enough redundancy in error correction that you don't notice it, right? I mean, even you reading this, there's some photons hitting the board and hitting back to your eyes. There's some evolution going on. It's not completely non-disturbive. It just does not disturb our encoding of the information. In the quantum case, everything is like a sleeping baby, and everything you do to it is like opening the door and making noise. And the goal is try to make this kind of be as quiet as possible when opening the door. But one thing is that if you woke up the baby, then the baby is awake. And if it was asleep, then it continues to be asleep. So if you measure something and then measure it again, you should get the same outcome. And this is true. So the rule now for what people call the collapse of the wave function is the following. So you take psi, you measure it, and you represent this by some projective measurement. And suppose that you obtain the outcome corresponding to pk. Then you disturb the state of the system. So the new state is this. And this is a rule for now. Later, we'll see a little bit about how it emerges. So it's the following. You took your initial state and you project it into this. You act with it with this matrix pk. Now, this ensures that if you measure it again, you'll see that because of the properties of projective measurements, you get the same outcome for sure. Now, the problem is that this is now not normalized. So this happened with probability psi pk psi. So you need to normalize this state, which again does not change the physics. It's just a convention to see how we do it, how we look at it. So, you know, if this happens with probability 0.5, we need to divide by the square root of that probability so that this is normalized again. So you normalize by the square root of the probability, which is this. Example, to see what it looks like. And I think we'll just do 2 examples and then I'll release you. So So let's suppose again that you have a continuous system, and now it's not a Gaussian, it's just some kind of state. So here's the wave function squared. And suppose it was in some kind of state. Okay. It doesn't need to be something physical, it's just, I mean, it is what it is, it's an example. All we know is that this area under here must be 1. And now suppose we measured and got this outcome here corresponding to this projector. So these are x0 plus delta. So we got this thing. The new state, the rule is essentially if you measure it, you should get the same outcome, but it should not change any other property of the state. So what you get is kind of a rescaling of this. So let's say something like this. Right, so you just take this part here. It's a very neat example. You take this part here and now you scale it up so that this area under here is again 1. Yes, look, suppose that this is the position of a particle. Where's the particle? I don't know. I know that it's squared by this wave function. I measure it. Oh, it's here. I measure it again immediately. It better still be here, right? In the same region. That's the idea. This is the rule. This is what people call the collapse of the wave function. We'll see a little bit later more details of this. But so the other examples that you can try at home is that in this thing we saw before when we had the qubit. So if you have this qubit, which was what, 0.90 plus 0.11, you measured in the Z basis, and you got, suppose with probability 0.9, you got outcome 0. So let's say we got outcome 0. So then what is the state it goes to when you get outcome 0? So call it phi 0. Well, then this is the projector. What's the projector here? It's just 0. This is 0. Psi, and then this whole thing divided by square root of 0.9, that was the probability, right? That's just this probability that we computed before. But when you apply this bra here to this state, well, this term goes away, so you just end up with square root of 0.90, 0.9, that's just 0. Meaning, look, you had a state that was in like this, what we call a superposition of 0 and 1, wasn't anything. You measured it in the 0, 1 basis, and now after the measurement, it is in state 0. If you measure it again, it will give you the, if you measure in any basis now, it will give you the outcomes consistent with being in this state. If you measured in the Z basis, got outcome plus, then you can do the calculations and see that you get a plus here. So in the discrete case, it's very easy. Like when you measure it with respect to the basis, after it's in that state. If you have a projector, because you have like some uncertainty about this region, it does not change the shape of the wave function in this region, but it just cuts off everything else, and then it rescales it. Yeah, there are questions? Yes.
Earlier you said that we may have noise, in which case our positions overlap slightly.
Yeah.
Would that mean that when the wave function collapses, we don't have this sharp couple?
Yeah, then you get something different. Yes, you get something different depending on, yes. So if you want to look it up, that's then you represent it by, instead of projective measurements, you represent by other objects called POVMs. And then it's a bit more complicated. Oh, it is. Okay. So before I let you go, like, it sounds strange, right? This is really this idea, oh, my measurement woke up the baby and now I have a awake baby and I need to deal with this. It's not just revealing information, it's really changing the state. And it makes sense if you think of those examples of how we actually measure, where you need to make it interact with something, right? You make it interact with a magnetic field, or you make it pass through some polarization filter or so on. So you're really like going there and touching the system to measure it. Later, we'll see that, a way to look at this is not that the state magically collapsed to 0, but that we became entangled with the state, and we'll like, maybe in 1 week or 2, we'll know what these things mean. Okay, so I'll end here, and we'll talk about observables next week as well. Thank you, and enjoy your lunch.